So what I was showing in this bit of the graph here was that I was suggesting that maybe the area under a velocity time graph is the distance. And we can go about understanding why that's the case in a moment, actually. But first of all, if we just say, well, if the velocity was constant, and then it was over a period of time, let's say the velocity was a constant at 3 meters per second, and it went for 5 seconds, then the distance would be, or the displacement would be, velocity times the time, which would be 15 meters. So what I'm suggesting is that actually this is the case whatever the situation, whether it's constant velocity or not. And I think it'd be good to, before we look at this graph over here, is to sort of try to prove why that's the case. So we'll just hop over to today's whiteboard to see if we can demonstrate that. So what I'm going to do actually is I think I'm going to steal these axes here, like that. I should have used the new lasso tool actually, but okay. So then I'm just going to rub out this bit here. Oh, I can't rub out the line yet, but I'll select that. And okay. Okay, so we've got an empty velocity time graph axes now. So let's say that the velocity was just all over the place. It went up and down like that, whatever it might be. What I'm saying is the area underneath that graph is the distance. So how can we prove that? Well, basically the way to do it is if you were to zoom in on this, you can imagine the area under the graph could be made up of an infinite amount of rectangles. So and the smaller and smaller you chop up those rectangles, the more. I mean, so if I just started off with like some reasonably big rectangles. Okay, so I basically produced a load of bar charts, and I'm saying approximately, if we said the area underneath each one of these bar graphs would probably be roughly the area underneath the graph itself, up to that point, of course. Now, clearly it's not though, is it? Because there's bits missing here, and there's bits not taken into account there, and so on. So, so if I were to make these bars thinner and thinner and thinner, I'd get a more accurate idea of where the graph is, of the area underneath the graph. So eventually, you can imagine it being infinitesimally thin, and you can imagine that the graph is going just like the speed's going along these bars, and then that would be for the duration of that. We can think of it as just a constant velocity over a period of time, and to calculate the area underneath would just be equal to that velocity divided by that. Multiplied by that time. So we could say that that bit there would be v. Let's say that's v2, and well, hang on. Maybe it's better to say that's t2. So the period of time t, and that would be velocity 2, right? So that's the velocity it was going at that time. So the area underneath that graph, or which would be displacement 2, is going to equal to the average velocity at that period of time multiplied by the average time at that time. Okay, does that make sense?